Hello, my darlings. Okay, so today we're looking at continuity versus differentiability. So a function is differentiable at a point if and only if the derivative of f at a exists. In other words, that limit as x approaches a of the average rate of change formula f of x minus f of a over x minus a exists. Okay? When you look at them, if the curve is smooth, rounded, and a continuous curve, those are our favorite. They are differentiable, okay? So the key to remember here, like limits, in order to be differentiable, f must be continuous and the left and right-sided derivatives must be equal. So you have to be able to show that the derivative from the left is the same as the derivative from the right. So you might write that the derivative at b from the right has to equal the derivative of f at b from the left. Sometimes that's a notation that you'll see also. Okay, so that we have to show the left and the right-sided limits are equal, very much like we did with continuity where we showed the limits were equal. Speaking of that, let's look at an example. We're going to take f of x as the absolute value of x. First thing we're going to do is f of x continuous at x equals 0, and then is f of x differentiable at x equals 0. Now we know this is the absolute value function. It looks like a v. We know this is a continuous function, but we're going to prove it. Now remember, the definition of absolute value is x when x is greater than or equal to 0, and it's negative x when x is less than 0. So when they ask us if the function is continuous at x equals 0, the first thing is, does f of 0 exist? Well, f of 0, we would plug it into the top piece and just get 0. Next thing is we'd have to show that the limit exists. So since 0 is the place where the pieces of the function change, we have to do the limit as x approaches 0. Let's do from the left of f of x first. That's the limit as x approaches 0. And from the left, that's the bottom piece of the function, which is 0, because negative 0 is still 0. And then we do the limit as x approaches 0 from the right of f of x. That's the top piece of the function, which is just x. And when we do the substitution, we get 0. Since those are equal, we know that the limit as x approaches 0 of f of x is 0. So we showed that the function exists, we showed that the limit exists. Now the third step is to show that this limit, x approaches 0 of f of x, which we found is 0, is the same as the function of 0. That works. Therefore, f of x equal to the absolute value of x is continuous at x equals 0. And we actually know that it's continuous everywhere because the top piece of the function is a linear function, the bottom piece of the function is a linear function, and linear functions are continuous because they're polynomials. So we now know that f of x is continuous everywhere. Now comes the new part. Is f of x differentiable at x equals 0? Now, we don't know the derivative yet, so we're not going to use the bottom piece. So if you have the function, this is the piece that you use. So if you have f of x, okay, if you have f prime of x, or you can find f prime of x, you can use the bottom. Now, I know we could probably find f prime of x, but I want to do this the harder way. So let's take a look. So to show that this is differentiable, we have to do the derivative at 0 from, let's say, the right first. So that's the limit as x heads to 0 from the right of f of x minus f of 0 over x minus 0. So that's the limit as x heads to 0 from the right. Now, f of x, when we're to the right of 0, is x minus f of 0 is 0, always, over x minus 0, which, by the way, that's just 1, and the limit as x heads to anything of 1 is 1, because the limit of a constant is that constant. Now, let's do the derivative at 0 from the left, which is the limit as x approaches 0 from the left of f of x minus f of 0 over x minus 0, which is the limit as x approaches 0 from the left. F of x this time is negative x minus 0 over x minus 0. So that's the limit as x approaches 0 from the left of negative x over x, which is negative 1. These are not equal. Therefore, f of x is not differentiable at x equals 0. Now remember, we were talking about the absolute value function, which is a v. That has a sharp corner. Okay, when we have a sharp corner, a derivative does not exist. That's why it wasn't differentiable, but we just proved it algebraically or analytically. Let's look at another example. Let's let f of x be x squared when x is less than 0 and x when x is greater than or equal to 0. So the first question is f of x differentiable at x equals 0? Now the first step, if it's differentiable, you first have to show that it's continuous. Okay, so the top piece of function, when the x's are less than 0, f of x is a polynomial and continuous. When x is greater than 0, f of x is a linear function, so it's a polynomial and continuous. So we need to check at x equals 0. So we do okay. F of 0 is going to be just 0. So the function exists. 2. The limit as x approaches 0 from the right of f of x. If we are to the right, then we're on the bottom piece of the function. We do substitution, we get 0. The limit as x approaches 0 from the left of f of x. We are on the top piece of the function now, so that's x squared, and 0 squared is 0. They are equal, which means that our limit as x approaches 0 of f of x is 0, so our limit exists. And finally, for continuity, we now know that the limit as x approaches 0 of f of x is the same as f of 0, so it is continuous. Next up, we're looking at differentiable. So if we want to know if we're differentiable at 0, we need to do, so 2, we're going to do differentiable. Okay. We're going to take the derivative 0 from the right, which would be this limit as x approaches 0 from the right of f of x minus f of 0 over x minus 0, which is the limit as x approaches 0 from the right, that f of x is the x because we're on the bottom piece of the function, over x minus 0, that's 1 again. The derivative 0 from the left, that's the limit as x approaches 0 from the left of f of x minus f of 0 all over x minus 0. That's the limit as x approaches 0 from the left of x squared minus 0 over x, which is the limit as x approaches 0 from the left of x, which is 0. These two values are not equal. Therefore, f of x is not differentiable at x equals 0. Now, let's take a minute and look at the other way that we could find this, whether or not it's differentiable. If we took the derivative of each piece, the derivative of x squared is 2x when x is less than 0, and the derivative of x is 1 when x is greater than 0. Notice I didn't put the or equal to because that's the piece we have to figure out if it's differentiable. Now what we can do is take the limit as x approaches 0 from the right of the derivative. That's the limit as x approaches 0 from the right of the bottom piece of the function, which is just 1. And then we have the limit as x approaches 0 from the left of our derivative, which is the limit as x approaches 0 from the left of the top piece of the function, which is 2 times 0, which is 0. Notice they're the same numbers we found up here. They're not equal, and therefore f of x is not differentiable at x equals 0. Both of those methods work. Okay, sometimes you'll be asked to use the definition of derivative. Sometimes they won't care which one. Sometimes one method is easier than the other. So now you've seen both ways to do it. Okay. But the one thing to realize here, guys, is that continuity does not imply differentiability. We know that if a function is differentiable, it's continuous. But just because a function is continuous does not mean that it's differentiable. And the absolute value of x is a perfect example of that. And here's a few more examples of how the derivative might fail to exist. Okay? The first one is when you have a corner, and that's that absolute value of x. It's the perfect example of you have a continuous function, but you have the sharp corner and the derivative does not exist at 0. Okay? Not differentiable at x equals 0 where it has the corner. Another one is when we have the cusp. Okay? So here's an example, f of x equals x to the 2/3. Again, right here at x equals 0, it's not differentiable. Another one is where you have a vertical tangent, because what is the slope of a vertical line? There is no slope. So if there's no slope for the tangent line, then there's no derivative. Because if you look, this tangent line is straight up and down vertical. That line has no slope. There's going to be no derivative. The next one is when it's discontinuous. So we know that if the function's not continuous, there's no derivative, because the left and right-handed derivatives are not going to be the same, or one of them won't exist. Okay? Now here's a new example. The graph of the function y equals f of x shown below is made of line segments joined end to end. We're going to graph the function's derivative and at what values of x between x equals -4 and x equals 6 is the function not differentiable. That might be the easier part. If you look, any place we have a corner, look for the sharp corners, because it looks continuous, everything's connected, but we have a sharp corner here, we have a sharp corner here, and we have a sharp corner here. That means there's no derivative at 0, there's no derivative at 1, and there's no derivative at 4. So that piece is the easy part. Now back to part A. Graph the function's derivative. Now, this function is made up of linear segments. Okay, all lines have a constant slope, and the derivative is the slope of the curve. So if we find the slope of the line, that will tell us the graph that we should be graphing. So if you think about this piece, it's going up 2 and over 4. It's rising 2 and over 4. So that slope is 1/2. So from 4 all the way to 0, but not at 0, so we need an open circle there. We have this horizontal line piece that has a height of 1/2. Okay, now this linear piece, this goes down 1, 2, 3, 4, and over 1. So this has a slope of -4. 1, 2, 3. So this is going to be way down here, and it's going to be open circles on both sides. Now we've got this piece in here has a slope of 0 from 1 all the way to 4. But remember, it's not differentiable at 1 or 4. we have this horizontal line that had a height of 0 because the slope of the function was 0. Now we've got one more piece here, and we're going to go up to 4. So it's rising 4 and over 2. So that slope is 2. So from 4, we're going to have an open circle until we get to 6. We'll have a closed circle and a horizontal line. So now those 4 horizontal segments together make the graph of our derivative. Nice. Just a couple of little notes here at the end. Most of the functions we encounter in calculus are differentiable wherever they're defined, which means they don't have corners, they don't have cusps, vertical tangent lines, or points of discontinuity. Their graphs will be unbroken, smooth, and a well-defined slope at each point. Smooth, rounded, continuous curves. We love them. Now, we know that differentiability implies local linearity, okay? So a good way to think of a differentiable function is that they're locally linear, that if you zoom in, the graph will straighten out and the graph will start to look like its tangent line, okay? Very close to that point of tangency. Now again, this differentiability versus continuity. Remember that in order for a function to be differentiable, it had to be continuous. This is a true statement. If f has a derivative at a, then f is continuous at a. The contrapositive, which switches and negates, we switch and negate the original statement. So it's not continuous, so this part came here. It's not continuous, then it's not differentiable. This is also true. If a function is not continuous, then it's not differentiable. However, some people just like to switch the original theorem. Okay, this is the original theorem, that if f has a derivative, then f is continuous. But if you switch it and say if f is continuous, then it's differentiable, that is not true. Continuity does not imply differentiability, and your perfect example is that absolute value function. Okay, so there we go. We've talked quite a bit about differentiability and continuity. Remember your 3 I's to prove continuity. Remember, to be differentiable, first you have to show the function is continuous, then you show that the limit of the derivative or the derivative itself from the left and the right are equal. Okay guys, have a great day. I'll see you soon.